You know how it is you interact with large language models, well, basically every single day now.
Yeah, absolutely.
Whether you're firing off a quick search query, chatting with an AI assistant, or maybe just using a handy summarizing tool, they seem to just, effortlessly understand human language.
They really do. It feels almost like magic sometimes.
But have you ever stopped to wonder what's truly happening under the hood? It's definitely not magic. It's actually this brilliant numerical transformation.
And that's exactly what we're diving into today. We're going to peel back the layers a bit and look at the fundamental building blocks, the real nuts and bolts that allow these powerful AIs to make sense of our words.
Okay.
We'll explore how these models convert our language into a format they can actually compute with, how they manage to keep track of word order even when it's all just numbers, and why these seemingly small details are absolutely critical for their incredible abilities.
And for this deep dive, we're pulling insights from some foundational research papers, practical guides, industry analyses, really trying to demystify these core concepts. Everything from, say, BERT token IDs to the pretty intricate world of positional embeddings. So get ready for some serious aha moments that hopefully will fundamentally transform your understanding of how AI truly works with language.
Let's do it.
Okay, let's unpack this then, starting right at the beginning. For a computer, our language, human language, it's just a jumble of characters, right?
Exactly. Meaningless symbols initially.
It's like trying to read a book where every single letter is its own separate thing. So the big question is, how does an LLM even begin to read something like a puppy is to dog as kitten is to? Where does it start?
Well, the very first step, the foundational layer, lies in something we call tokens.
Token.
Yeah. Think of a token as the smallest meaningful piece of text an LLM processes. It's often a whole word, like puppy or kitten.
Okay.
But sometimes, crucially, it's just a part of a word.
Ah, okay. And that's where something like BERT, Google's influential language model comes in.
on there.
It uses a specific method, right? Word piece tokenization.
Precisely, word piece tokenization. And it's a really clever technique designed to intelligently break down text into these manageable tokens.
How does that work then, like in practice?
So take a word like unbelievable. Using word piece, it probably wouldn't be treated as one single unit.
Right.
It's often split into something like and then hashtag believable.
Ah, the hashtag bullet. What's that about?
That hashtag tag isn't just decoration, it's a visual clue, basically, telling the model that believable is a subword and is connected to the piece that came right before it, in this case.
Okay, got it.
And this whole strategy is incredibly smart for handling new or rare words the model hasn't explicitly seen during its main training. It can break them down into known parts.
So that deals with novelty. That makes sense. So, okay, we've got these clever token chunks, these words or subwords. How do we bridge that gap from, text like to the numerical language a computer actually speaks?
That's the next critical step. Each one of these tokens gets converted into a unique number. We call it a token ID.
The token ID.
Yep. It's basically like giving every single word or subword in BERT's massive vocabulary its own distinct digital fingerprint.
Okay.
So for our example sentence, a puppy is to dog as kitten is to, each word, plus maybe some special markers BERT uses, gets its own unique ID number.
So puppy gets an ID, gets an ID, two gets an ID.
Exactly. And importantly, every time BERT sees puppy gets the same ID. Same for is, same for to, even though they appear twice.
Right, consistency. But why? Why go through all this numerical gymnastics? Why is this conversion so fundamental?
Well, there are really three core reasons this numerical conversion is pretty much non-negotiable for models like BERT.
Okay.
First, and most basically, computers speak numbers. Neural networks need numerical input, not raw text. Token IDs are that essential bridge.
The interpreter.
Exactly. Second, it's about efficiency and scale. Think about it. Words have different lengths, right? But IDs are uniform. Fixed-length IDs allow models to process sentences of varying lengths much more uniformly, much more efficiently. Essential when you're dealing with massive data sets.
Okay. That makes sense. Speed and scale.
And third, and this goes back to the word piece thing, it helps handle the unknown. If a word isn't in the model's main vocabulary list, word piece tokenization can often break it down into familiar subwords that do have IDs.
Ah, so it rarely gets completely stuck on a totally new word.
Exactly. It prevents the model from encountering truly unknown words most of the time, and that's a huge deal for flexibility and robustness.
Okay, so we've transformed words into these unique numerical IDs. We have a sequence of numbers, but like a string of numbers alone doesn't give us meaning, does it?
Not on its own, no.
The real challenge, maybe the real magic, seems to be how these sequences come alive with context. How does BERT turn that sequence of numbers into actual understanding?
Precisely. And that's where the deeper processing inside the model, inside BERT, truly shines. Those token IDs we just talked about.
Yeah.
They get passed through multiple layers within the BERT model, complex layers of neural networks.
Okay.
And in these layers, BERT learns the relationships and meanings of words based on their neighbors.
Yeah.
And crucially, not just looking one way, like left to right, BERT looks bidirectionally.
Both ways, left and right at the same time.
Yes, scanning both left and right across the sentence simultaneously. This bidirectional understanding is really key for tasks like masked language modeling.
Masked language modeling.
Yeah, it's a core training technique where you basically hide a word in a sentence, you mask it, and train the model to predict what that hidden word is, just based on the surrounding context.
Oh, okay. So if I gave it something like a puppy is to dog as kitten is to mask, it would use the numbers for the other words to figure out the mask.
Exactly. Based on the surrounding token IDs and the patterns it's learned from seeing billions of sentences, BERT can infer that the masked word should probably be cat. It understands that analogy, that relationship, purely from the numerical context.
Wow.
And this capability, this contextual understanding derived from numbers, is fundamental to how LLMs power so many tools we use now, chatbots that seem to get what you're asking, search engines giving relevant results.
It all comes back to these contextualized numbers, but hang on, there's a critical challenge here, isn't there? You mentioned BERT's architecture is based on the transformer, and I remember reading that a plain transformer model, at its core, doesn't inherently understand the order of words.
That's absolutely correct. It's a key point.
It's like if you just threw the words, the cat chases the dog into a bag of words, you lose the meaning completely, right? The dog chases the cat is totally different.
Completely different money. The raw transformer mechanism itself is permutation invariant. Shuffle the inputs, you get the same initial representation, which is obviously not how language works.
So how do LLMs handle this fundamental problem? How do they know cat came before chases?
This is where position information becomes absolutely essential. Without encoding position somehow, models would be lost. Syntax, grammar, semantics, they all depend heavily on order.
Okay, so how do they encode it?
There are two main sort of elegant ways to tell a transformer where a word actually sits in a sentence.
Two main ways, okay.
First, we have what's called absolute position embeddings, or APE.
Absolute, like its exact spot.
Exactly. This method directly encodes the precise position of each token in the sequence. Position 1, position 2, position 3, and so on. The original transformer paper used a clever approach here, often using fixed mathematical patterns like specific sine and cosine waves, unique to each position.
Sinusoidal patterns, why waves?
It's a neat mathematical trick. These wave patterns allow the model to potentially generalize to sequence lengths that it hasn't seen during training, and they give each position a distinct but related signature. Other models, like BERT, actually learn these absolute position embeddings during training rather than using fixed ones.
Okay, so that's absolute position. What's the other way?
The second main approach, which has become very influential, is relative position encodings.
Relative, so not the exact spot, but compared to other words.
Exactly. This method shifts the focus from a word's exact numerical address, like position 5, to its distance or relationship to other tokens nearby.
Okay. Can you give an example?
Sure. Think about our sentence. The cat chased the dog. Now imagine you had a word at the beginning. Suddenly the cat chased the dog.
Right.
In an absolute system, the positions of cat, chased, and dog all just shifted by 1. They're now in positions 3, 4, and 5 instead of 2, 3, and 4.
Okay.
But with relative position encoding, the relationship between cat and dog, how far apart they are, and their order relative to each other remains exactly the same. Dog is still 2 steps after cat.
Oh, I see. It focuses on the distance between words. That feels more intuitive for language somehow.
Many researchers think so. It's less about a fixed seat number and more about the connections and distances between the words themselves, which often carries more semantic weight.
So just to get this straight, absolute positioning was foundational, but the move towards relative encodings, and you mentioned some models even combine them.
Exactly. That's the cutting edge. Researchers are constantly refining this. Some advanced models, like BERT, for instance, effectively combine both absolute and relative position information.
Why both?
The argument is that they might be complementary. Absolute position gives you the overall location, while relative gives you the local context and relationships. Combining them might offer the best of both worlds and seems to boost performance on many tasks.
That makes sense. And it's not just about simple linear sentences anymore, is it? I've heard about position information being used in more complex data structures.
Absolutely. Think about language not just as a line of words, but sometimes as a graph, like a dependency tree showing grammatical relationship.
Okay, like subject-verb-object connections.
Precisely. In those cases, positional encodings can be designed to represent things like the path length or the structural relationship between words in that graph, not just their linear order. This helps LLMs grasp deeper semantic connections.
So it goes beyond just word number 3.
Way beyond. And there are also specialized positional encodings used in the decoding part of models, the part that generates text. These can help control things like the desired length of the generated output, or even enable models to predict words in a different order, not just one after another, which can speed things up.
Fascinating how flexible this concept of position can be. Okay, we've seen how position works from simple lines to complex graphs. But let's zoom in even further, right down to the building blocks of language itself. What's the relationship between these LLM tokens we talked about, these often subword units, and the things we think of as the smallest meaningful units in language, like morphemes?
That's a great question. Morphemes being things like prefixes, suffixes, root words.
Exactly. Are the subwords that models like BERT learn using word piece or byte pair encoding the same as linguistic morphemes?
Interestingly, no, not directly. It's a common misconception. While the algorithms like byte pair encoding or word piece break words into frequent statistical substrings, these don't necessarily align cleanly with linguistically defined morphemes, which are based on meaning.
Can you give an example?
Sure, like we said, unbelievable might become un and hashtag believable as a morpheme, but say the word dogs might just be a single token, even though it have the root dog and the plural morpheme s,
Right.
or a word like racket might get split into rack and hashtag es, which doesn't really map to meaningful morphemes at all.
So the model's units are based on frequency and statistics, not linguistic meaning structure.
Primarily, yes.
Yeah.
And this difference is actually a really active area of research. Does this mismatch matter? Some studies suggest it has limited impact on overall performance for many tasks. But others argue that developing more morphologically aware tokenization methods, ways of splitting words that do respect linguistic morphemes more closely, could lead to better generalization, especially for understanding semantics, and particularly in languages that have really complex morphology, lots of prefixes and suffixes.
That makes sense. It feels like aligning with the natural units of meaning should help. Okay, what about even smaller? What about the individual letters within a token? Does an LLM know how a token is spelled? I ask because, sometimes you see LLMs make weird mistakes with simple things like counting characters in a word.
Right. It's a truly fascinating paradox, isn't it?
Yeah.
On the one hand, LLMs can indeed struggle with explicit character-level tasks. There are famous examples where a model might be asked to count the letter I in a long string of I's, and it gets it wrong,
Yeah.
sometimes confidently wrong.
Like saying 29 eyes is actually 30 eyes or something.
Exactly. Which makes you think, okay, it clearly doesn't understand characters. But other research digs into the model's internal representations, the embeddings for each token, and finds that they actually do contain quite a bit of implicit information about the characters within that token.
So it struggles with explicit counting, but internally it kind of knows the spelling. How does that work? That seems contradictory. What could be going on there?
Well, one compelling hypothesis ties back to tokenization variability. Think about a root word, like dictionary. Depending on the sentence it's in, it might get tokenized slightly differently sometimes. Maybe dictionary sometimes, maybe diction and hashtag airy other times.
Okay.
This variability, the hypothesis goes, might actually force the model to learn the underlying character patterns to make sense of these different tokenizations, all pointing to the same core concept. They have to implicitly figure out that diction plus hashtag airy relates strongly to the single token dictionary.
Yeah.
It's almost like it has to learn to look inside the token representation.
Like learning from noisy or varied input forces a deeper understanding.
Exactly. It's somewhat analogous to how robust speech-to-text models learn. They hear words pronounced slightly differently all the time in noisy environments, and they become good at recognizing the core word despite that variation. The LLM might be doing something similar with character patterns due to tokenization fuzziness.
That's a huge insight. It's not just ignoring the characters, it's learning about them implicitly because of how the tokens sometimes shift around. Oh. Okay, so knowing all this, how tokens are made, how vital position is, even how characters might be implicitly represented, how does this deep understanding empower us when we want to fine-tune an LLM for a specific real-world problem, say in medicine or finance?
This is where understanding these mechanics becomes really practical. It leads directly to the concept of domain vocabulary.
Domain vocabulary, meaning the specific words used in a field.
Precisely. For specialized areas like medicine, law, finance, engineering, just using a general-purpose LLM often isn't enough. It might not know the specific terminology, the jargon, the nuanced meanings unique to that domain.
Right, it might hallucinate or misunderstand specialist terms.
Exactly. So you need to explicitly teach the model the language of that domain. And that starts with building a specialized vocabulary. This involves, meticulously analyzing industry documents, maybe textbooks, research papers, consulting subject matter experts, finding all those crucial terms.
And how do tokens and tokenizers play a direct role here in this fine-tuning?
It's crucial. Once you have your list of important domain terms, maybe specific drug names, financial instruments, legal concepts, you can often create custom tokenizers.
Custom tokenizers?
Yes. You can configure the tokenizer specifically so that these important multi-word terms, or complex single words, are treated as single indivisible token units by the LLM.
Ah, so non-small cell lung cancer becomes one token, maybe, instead of being chopped up.
Exactly. Or a complex chemical name, or a specific financial derivative. By making it a single token, you help preserve its precise meaning within the model and prevent it from being misinterpreted by being broken into potentially misleading parts.
That makes a lot of sense for accuracy.
Definitely. Then you integrate this custom vocabulary and the custom tokenizer into your fine-tuning process. You prepare training data using this tokenizer, ensuring the model sees these specialized terms used correctly in realistic, domain-specific sentences and contexts.
So the whole process, finding terms, organizing them, creating the custom tokenizer, building the right training data, it's all about giving the LLM the precise numerical building blocks it needs to achieve deep understanding in that specific domain.
That's the goal. Equipping it with the right vocabulary represented in the right way numerically allows it to perform much closer to an expert level within that specialized field.
Wow, what an incredible journey we've taken today. We started with just breaking text into these small pieces, these tokens.
Seems simple at first, right?
Yeah. And then we saw how those tokens get unique numerical ABs, how those numbers feed into the model's layers to build up contextual understanding, looking both ways.
The bidirectional context, yeah.
And then how absolutely critical position information is, whether absolute or relative, allowing the model to grasp the subtle, crucial dance of word order. It really is far more nuanced than just, matching keywords.
It really is. And we've seen how sophisticated the research is becoming, constantly refining these techniques, handling longer and longer sequences more efficiently, dealing with complex graph structures, not just linear text.
And those surprising insights, like how models might be implicitly learning about the characters inside their tokens, even if they can't count them perfectly.
Right. This deep dive into the mechanics, into the plumbing of LLMs, it truly shows how these models work at a fundamental level and helps explain why they are so powerful. It's quite profound when you really think about it, how all this complex linguistic intelligence seems to emerge from these essentially numerical transformations and positional cues.
So as you, our listeners, continue to interact with LLMs in your daily lives, remember that beneath that smooth, often remarkably human-like conversational surface, there's this intricate symphony playing out a symphony of numbers, tokens, embeddings, and precise positional understanding.
Well put.
And maybe here's a final thought for you to ponder on your own. If LLMs can learn so much about language structure, about meaning, about relationships, just from these numerical representations and their positions, what other hidden rules or strictures of human communication, things beyond just words and syntax, might they eventually uncover and replicate?
That's a fascinating question.
Think about, say, the subtle cues we use in tone of voice, or the unspoken subtext in a conversation, or even how information is laid out visually on a page. Could those kinds of elements also, perhaps, be encoded and understood through similarly intricate forms of positional or structural information in the future? Could that give LLMs an even richer, more holistic grasp of our world?
Something to think about, definitely. Where could this numerical representation of information take us next?